It's an honor to introduce Raquel. Raquel Urtasun, Chief Scientist at Uber ATG, and Associate Professor at the University of Toronto. She's been all over the place. You've been in many places, right? So originally from Spain, PhD in 2006 at the PFL, and then you've gone through even a couple years here at MIT, Berkeley, at Zurich, in Chicago, and finally in 2014 got a position at the University of Toronto, which was kind of in the midst of that exciting ecosystem in Toronto and in Canada in general for AI, where Raquel has been sort of like a key player in many of the things that have happened. The Vector Institute, she has a Canadian chair for machine learning and computer vision, and sort of especially, and maybe most relevant to this talk, in 2000, like about 3 years ago, she was instrumental to crafting this kind of unique relationship between a university and a company, which is Uber ATG, right next to Toronto University, University of Toronto, where she's chief scientist. Very interesting relationship between those two worlds. Maybe you probably know Raquel already for many things, but maybe one of the things that you know her the most is sort of this Kitty data set or benchmark, which was a CVPR paper in 2012, I think, and then IGRR in 2013. And basically sort of brought up the question as to whether sort of the performance that the traditional algorithms in computer vision were having were really a thing or were just a byproduct of the biases in those data sets. So she provided a data set in a much more unstructured environment, so it was captured with an actual car driving around, and demonstrated that sort of the performance was actually dropping quite considerably, sort of bringing up the need to work on more realistic environments. So I don't know how much of that sort of drove you to start working with Uber. But I'll leave it just with one question, which is actually not my question, but it was your question, which is at the title of the Kitty paper dataset, which was, are we ready for autonomous driving? I was rereading today the paper, and I don't think you answered the question in the paper. I don't think you give a straight answer. So, are we?
Let's see, big pressure here. I think we have made big strides, and hopefully today I will show you some of the great work that my students have been doing, pushing the frontiers of what self-driving was towards what self-driving should be, and hopefully where we need to go in the future. So thanks for the kind introduction, and it's really a pleasure to be here. Last time I was here was 14 years ago almost. It's been a long time. That reminds me how old I am. But at the same time, Seattle was the first place in North America that was my home, and this was very, very interesting. Cool, so today I'm gonna be talking about, as I mentioned, what we have done in the past, maybe 2.5 years in terms of self-driving in my research lab, which is part of Uber ATG, which is a big program in self-driving with many people. And I'm gonna stay quite high level today because I wanna give you more of the intuitions of why we did the things that we did and what are the open problems, but more than happy to go into more details if you have questions. So the first thing to sort of think about is if you want to do self-driving at the scale, and here we're talking about Uber scale, right? It's a very, very large scale. There is really like 3 components that you need to think about. On one side, you need the physical, the body, right? So you need to be able to build these vehicles at the scale, and these vehicles are not just regular vehicles. At the same time, you need to be able to develop the brain of the self-driving car that is able to operate in very complex scenarios and environments, right? That is able to react to many different things that can happen in the real world. Now, what is important to note is that it's not just about building cool technology and being able to also fabricate these vehicles, but also we need to deploy them and create a product that people are going to use. Now, with self-driving, what's happening is that we're going to see that the ownership of cars is going to go away fully, and it's really fleets, and you're going to have a service. And this is going to allow us to share the resources of the environment, which is, of our planet, which is actually a good thing. Cool. So at Uber, we know about how to build these networks to dispatch things, right? And we are partnering with car manufacturers in order to build these robots. We have a deep collaboration with Volvo. You will see some of the prototypes here. And we develop a lot of in-house. We develop the brain of the car as well as compute, et cetera. Cool. So the robots that we have, this is my only hardware slide, so sorry for the hardware people here. So we have these amazing robots that basically have an overcomplete set of sensors. And the reason why we have an overcomplete set is that we don't want to limit the space of possibilities, right? The solution to self-driving at scale does not exist yet, right? And we need to be able to get there, and in order to get there faster, right? So we don't want to limit what those sensors are. So we have LiDAR sensors on top of the vehicle, as well as high-definition cameras that both see 360 degrees around the vehicle. We have ultrasonics, we have radar, et cetera, right? So that have very, very complementary information. We have a customized compute that sits on the trunk with some really cool cooling, such that you can do a lot of processing. Everything is neural net based, right? So there is a lot of stuff that goes into the computation as well. Now, what do these robots actually see? So here I'm illustrating two of the main sensors. On the left-hand side, you can see, you can see what the cameras see, and on the right-hand side is LiDAR point cloud, see from the top. So imagine you were in the sky looking down, right? And the first thing that you can see, right, is that these sensors are extremely complementary, right? The LiDAR is fantastic at giving you 3D positioning, right? And the images are not so good at that, right? But they're very good at giving you semantic information about the environment, right? So this is one of the reasons, right, also why you want to fuse and use all these different sensors. Now, radar is fantastic at giving you velocities, for example, right? So that is also very complementary to any of this information as well. All right, so now, as an AI person, right, the first question to ask is, well, sure, I can solve this task with AI. Now, the question is, in practice, how do I do that? So there is like two different philosophies of how you can do this. One that you see a lot in academia, as well as some of the startups, is to say that, well, I can capture data, right? And I can train a neural network that takes the sensor output as the input to the neural network. And then this network can basically spit out my control commands, right? Whether it's acceleration, a steering command, et cetera. Right? The advantage of doing something like this, right, is that it's very easy, right? It's a few lines of code on your favorite, TensorFlow, PyTorch, whatever is your favorite language, right? So that's great, right? But at the same time, the problem is that it's going to be actually really difficult to bring that little prototype into something that is safe, can scale, and work everywhere in the world, right? And some of the issues here is that you don't have compositionality. It's very hard to understand when you make a mistake how to improve this, apart from saying, maybe I should change the architecture, right? Instead, you don't have so much insights into how should I do this problem better. And it's very, very important that for us that we have explainability, because imagine something goes wrong, right? We need to be able to explain into what was the thing that made the system actually do something that is potentially catastrophic. So this is, some of the reasons that, yes, it's very easy to get a prototype, but it's very hard to actually get something to work that is the real thing. And we want to have, many, many, many vehicles all over the place in the world, right? So the alternative that we see is what you see in industry and almost every player, which is more of a traditional software stack. And the way that this works is the following. You have the output of the sensors. I'm illustrating this here with the LiDAR, okay? But you have the other sensors as well. And the first thing that we all do is that we basically localize the vehicle, okay, where it is in the world. And the reason that we localize the vehicle is that we want to use our prior knowledge about the environment before we even see anything from the sensors, right? So here I'm illustrating the map with some of the components, for example, where the lanes are, traffic lights, crosswalks, all that stuff, right? So before you even see, you have all this knowledge about what the environment. That can allow you to actually plan farther away, right, beyond what the sensors see, as well as be more careful into, maybe I should pay more attention here, maybe potentially there is more density of pedestrians or whatever. So once the vehicle is localized, then typically what you do is you do perception, right? And perception, basically you want to estimate the categories of interest as well as potentially other stuff that is happening in the scene, right? So here bounding boxes are vehicles and pedestrians are these circles. And you need to do this in three-dimensional space. Okay, this is different than what you see also in many academic papers, which is in the image domain, and Kitty was very biased towards image domain as well. But this understanding the present is not sufficient for self-driving. We need to also understand the past because we want to understand motion, how these things move in the environment, right? So typically this is done within tracking or some of these frameworks. But this yet is not sufficient, right? If you want to plan a safe maneuver, you need to somehow understand how the future might unroll, right? And that's typically called the prediction problem, okay, in self-driving. And the idea is that here I'm highlighting this with waypoints, and this is basically the most likely trajectory of where these actors might go in the near future. Now, typically you do this with multimodal distributions, but for illustration purposes, so bear with me, this is a single trajectory per actor, okay? So basically, we do reasoning about the past, reasoning about the present, and reasoning about the future. Now, once we reason this way, right, we are ready to say, well, there is a region of interest around us that we can actually reach in the next few seconds. Now, we want to plan a trajectory that is safe given all these things that are happening in the environment, okay? And we do this replanning at every cycle, basically, okay? Now, motion planning is not the end of the stack, and the reason why is that you might plan a maneuver, but maybe the car is not able to execute exactly this maneuver. Maybe you don't have the right vehicle dynamics. Maybe there is friction. Maybe there's something else where there's an error, right? So what happens, right, is that you use control in order to bring what the car does to what you intended to do in the first place, okay? So what are the advantages of such a system is that now we have compositionality and we have modularized what we need to do so we can actually divide and conquer, right? And that's typically what you see in industry is that you have teams of hundreds of people in every one of these modules developing the stuff. And we can incorporate our prior knowledge because this is very reminiscent to how we think about the environment, right? So that's a positive. Now, what is the negative in doing something like this? So there is a few problems. One is that typically, since you have these gigantic teams, what happens is that they agree on an API into what is the information that is going to be passed from one module to the next. And this information typically is extremely simplistic and small. Typically, for example, if you detect the vehicles or the actors in the environment, you pass vehicle state, maybe the past trajectory, maybe some notion when you have prediction of where you might think that is going into the future, but you have lost so much information already. So what happens if you actually made the wrong prediction, if you make the wrong detection, right? It's impossible for the system to correct for your mistakes. Now, the other thing that happens is that the reaction time of the vehicle has to be extremely fast, right? And there is a lot of compute that needs to be done, and there is a lot of modules here. So you need to make a lot of compromises into what those modules are in order to reach the compute time that is, say, a few milliseconds, right? So you're not going to use the latest, greatest, blah, 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 right, because it's too slow. Instead, you're going to do something that is actually more simplistic. Now, the other thing that is important as well is that these teams are developing typically these different models, right? And they are basically just thinking about that problem in isolation of everything else. Okay, so if you look, for example, and this was also my fault when I created Kitty, is that we say, okay, we have a detection challenge, and we're going to measure average precision, right? And that's the way that we're going to rank and score everybody. Now, what happens in self-driving is that, well, if you look at the scene, every actor is not equally important. Right? So this aggregate metric that basically tells you that you should detect everybody equally well is actually not the task that you need to solve. Right? Imagine, for example, that you need to pass between two vehicles and you have to squeeze by. You need to really understand their shape really closely, or you're going to maybe bump into them. Right? However, if there is opposite traffic that you have already passed, you're never going to interact with that vehicle. So it doesn't really matter whether you detect or not that vehicle well. You might want to detect it because there is interactions with other things that might be closer to you, right? But at the end of the day, what happens is that this way that we train the systems is not the way to really get to the performance of the full system that you need to. Okay? And what also happens is that as the engineers are, as I mentioned, there is a lot of people working on this. There is a lot of changes that go on the stack, right? And this is going to affect everybody else's. So you end up, engineers changing the tail of other engineers, and people saying, hey, I make this change, maybe it affects your motion planning, right? And this is one of the reasons why the progress has been relatively slow in the past few years. Make sense? All right, so what are we trying to do at Uber that is different from these two traditional or these two approaches? So we are trying to bring something closer to something in between, right? So what we like to have is a single AI system that is end-to-end trainable, that is able to do the full thing, but at the same time is doing this through reasoning, right? The traditional stack, typically a motion planner does reasoning, and that's a good thing. We don't want to lose that bit. At the same time, we want to generate intermediate interpretable representations so that we can meet our safety requirements and we can prove safety as well. We can have decompositionality in testing, for example. And as I mentioned, we want to learn this with a push of a button because we don't want to rely on engineers talking to engineers. Hey, there's a change. It might affect your thing. Instead, the system should self-correct for the end goal, right, and train all the different parameters such that you are optimal for the task at hand, which is to drive safely and as comfortable as possible, given safety. Now, what is also important is that by doing something like this, you can use the sensor data for any one of these subtasks, right? You haven't compromised, and you can share a lot of the computations through the different tasks. And that allows you to potentially have much more complex algorithms in the same time frame, or even faster than the traditional pipeline. You can incorporate prior knowledge because you have these intermediate representations, and a priori, this is a much simpler system that traditional stacks have hundreds of thousands of lines of code, millions of lines of code, which is extremely complicated in this expert system to understand how all these things relate to each other, okay? All right, so let me tell you a little bit on, this is the vision of what we're trying to build into the different generations of things towards achieving that vision. So we started by building perception algorithms that first started with lidar only, because it's the main sensor that is the strongest sensor, despite being a computer vision person to start with, to my despair. And then we build more and more generations that were able to actually blend information between the multiple sensors as they go. And it's important that it's neither early fusion nor late fusion, right? Instead, the network can learn to collect and grab this information from the different sensors as it goes through different levels of processing, right? Because depending on the level of semantics or the representation, right, you want to fuse this information in different ways. So that was important. And here what I'm showing is one of our latest, greatest object detectors. So it's 3D, right? Uses all this. So it uses cameras as well as images. And you see here it's multi-class. It runs in a few milliseconds on the vehicle. Okay? So you can achieve very, very high levels of performance, right, while exploiting all these different sensors. Now, what is important to note is that by doing object detection, you're not going to solve this task. And the reason why I say this is that it's not safe to only drive with detection. So detection is something where you decide on a threshold and you put bounding boxes around objects. But there might be evidence that there's something there, and if it's below your threshold, suddenly you're going to run into something, right? So we build systems that instead of just doing detection, they not only do that, but they also explain all the different pieces of evidence. So for every lidar point, you want to explain what it is. In this case, I'm showcasing this by showing some of the categories that we can reason about, which is the road, background, and the different actors of interest. You can do the same thing for images, right? And then basically explain every single pixel, right? And for images, it's important that you do something that in the academia is called panoptic segmentation, right? Where you not only estimate the classes of is this a car versus not, you also delineate that this is a different car than this car next to me, okay? And this is a way that, again, you try to explain this is what we can do these days real time on a single, with a single image. This is independent per frame, yes, to show that. Now, there is a lot of work that you see in the literature, right, about how to do detection of certain categories of interest. However, if you work in self-driving, in the world, there is so much stuff that actually happens on the road that potentially can interact with the vehicle, right? Like, for example, here is a deer in front of our vehicle, right? And the question is, should I build a deer classifier? What about a moose, a hippo? What about a matrix that falls off the car that is driving in front of me, right? So it's impossible to be able to build all the possible categories in the world, right? So we need to have a safe fallback system that is able to not only understand the categories of interest, but also that is able to say that there's a thing there. Maybe I don't know exactly what it is, but maybe I know the physical properties, I know how it's moving, I can estimate how it's going to move in the future, and I can plan a safe maneuver based on this thing, okay? Now, in the literature, what you see also is that people build different systems, one for detection, or one for this category, and another one for rare objects. And the problem then is that you need to have a fuse operation that is able to decide into, should I try this system or should I try that other system? And if you do this, then you're making this very complex decision with almost no evidence, right? So you're already losing. Instead, what we do in the lab is we try to build single algorithms that are able to do all this reasoning together so that you don't need to have a second system trying to make a decision for you. And that's, as you train the whole system, this is actually safer. So in terms of this, so you can train object detectors and at the same time train embeddings for every one of your, in this case, representation with later points, such that independent of what they are, you can actually merge them together or cluster them together if they belong to the same instance. And that's the way that you can do semantics, right, at the same time as grouping things that you don't necessarily know what they are, okay, within a single network. So as I mentioned, right, this is the concept of open set segmentation, where you want to understand known things, you want to understand unknown things, and at the same time, unknown stuff, for example, the road, right? There is countable things, uncountable things, and things that can happen that you don't know what they are. And so you can lift these representations such that you can cluster them, and at the same time, they maintain the categorization for those things that you know what they are. Cool, so this is just showing a little video of, we can do root, we can do semantic classes, and you see popping up things that basically are different instances that, although we don't know what they are, they can be segmented automatically. Okay. We can do dogs this way, we can do our deer, etc. Okay. This is a very interesting direction. This is really just a first prototype. There is so much to be done on this direction, and it's very important. All right, so this is all about perception, right, what I talked about so far. But I mentioned that we want to have a single AI system that is able to do the whole stack. So let me build that little by little for you. So the first thing that we look on that domain was, instead of trying to do everything, right, and you're lacking the insights, we take smaller problems and we build into bigger problems, right, as you build your intuitions. So we build systems that at the beginning could do perception and prediction, could understand the past, the present, and the future, okay? You can do this within a single network in a few milliseconds, and I'm just going to show you the results here. So on here, what you see here is, so as you drive, right, you're detecting all the different vehicles in this case, where we place these bounding boxes in three-dimensional space. The color indicates that they are tracked over time, so that is the same, you understand their motion, right? And the little dots emanating for every one of these vehicles is basically our predictions into the future. Okay, this is the first version, which we call Fast and Furious, which was able to estimate short-term predictions. But you can see here also the difficulty of doing self-driving, right? There is so much stuff, so much occlusion, right? It's extremely difficult to get results of this level. Now, we can go one step forward, right, in terms of the prediction, and in terms of motion planning, we would like to not only understand how things are going to move potentially in the future, we will also want to understand their intention, right, so that we can use that in terms of better planning. So in this case, it's a single network, again, that's detection, prediction, as well as intention, okay? And I want you to focus, there is a lot of stuff happening in this video, so sorry for that, but I want you to focus on the bottom, okay? And what I want you to see is that the different colors of the different detections are basically a probability of the different intentions. The more red it is, the higher the probability of arriving to a stop. The more purple it is, the higher the probability of being parked, as you see a whole bunch of parked cars here. And the more yellow it is, the higher the probability of continue driving, right? So the difference between park and stop is quite a nuisance, but it's very, very important for self-driving because what you will do as a planner will be very different in these two scenarios. Now, with the arrows also emanating from the different vehicles, what you see is also some other types of intentions, whether we're going to keep lane, whether we're going to make a turn, whether it's left or right, or whether potentially we're going to change lanes. Okay? And you have this multimodal distribution over all these intentions. And now, condition on the intention, you can predict your most likely trajectory, and you have a multimodal distribution this way. Okay? And what I'm showing you here is this system actually running on vehicle. Okay, so this is what is very interesting is that you can take the research that you can write interesting papers and whatnot, but actually this stuff runs on production systems, and that's the very interesting thing about the setup with Uber. And here I'm showcasing a particularly difficult scenario where which happens quite a lot, right? It's during the night, and our cities, right? There is so much stuff happening, right? There's so many vehicles here. There's so many pedestrians, right? And here we are able to predict nicely where they are, what they're going to be doing in multimodal distributions, including some illegal maneuvers by some of the vehicles that were U-turning in this case. So this this shows how difficult driving is, but this is just one scene, right, of the many scenes that you need to handle properly. So this was about joint perception and prediction. Let me tell you a little bit about what we did in motion planning. And let me illustrate motion planning first by giving you an example. So this is our vehicle driving around, and it arrives to this case where basically there is a parked vehicle, right? And in order to continue its route, the self-driving car has to go in the incoming lane, which is a very dangerous maneuver, right? And basically just go around this vehicle. So you want to be very careful into when you do this maneuver, right? And in this case, there was an oncoming traffic, right? So I need to reason about we don't have enough time, right? We need to let them pass, and then we can go around into incoming traffic. Now, this to you might seem like an easy thing. Like this level of reasoning is not so easy with AI, right? So the question is, how can we do that with modern techniques? So the way that our planners or motion planners typically work is as follows. So given a situation, in this case, I'm showing you two different scenarios, right? There is typically a behavioral planner that decides what is the type of action I should be doing. For example, should I ACC behind this car or should I pass? Right? And condition on this decision, there is typically a trajectory planner that is going to choose the best trajectory to do for the self-driving car in order to drive safely and arrive to the goal, etc. Okay? Now, the problem of such a thing, right, is that you have a behavioral planner and a trajectory planner, and both things are not necessarily talking to each other correctly, meaning that the behavioral planner is optimized or is a very different algorithm from the trajectory planner, right? And as a consequence, they might do inconsistent decisions because they don't optimize the same objective, right? For example, this guy could say, oh, I'm going to change lanes, but then suddenly the trajectory planner that is trying to really say, okay, now that I know that I want to change lanes, what is the trajectory? Maybe there is no feasible trajectory, right? And then what do? This is not safe, right? So one of the things that we look at is, well, instead of doing this, these separate models for behavioral planning and trajectory planning, instead, why can't we build a system that basically has the same objective, and it's just a matter of how you do inference on that objective, right? Because at the end of the day, the reason that you do behavioral planner is because it's too costly to do very fine-grained trajectories all over the place, right? But the objective itself, you're trying to do motion planning, should be the same, right? And that way, at least it will be consistent, right? And you will have this notion of whether you can execute that behavior or not. And the other thing is that you can actually learn motion planning. There is no reason why you have to hand-tune these weights, which is typically what is done in industry. Okay, so we can do an end-to-end learnable motion planner, right, that actually does behavioral planning as well as trajectory planner. And the idea is that you can think of behavioral planner as I wanna basically explore the space, right, so that I have coverage. And the trajectory planner is gonna refine the possible solution, or maybe you can maintain multiple modes and refine those modes so that no matter what, you always have a safe maneuver. Okay? And you can think of this as sampling versus optimization within the same objective function. And that's just a particular inference algorithm for this task. So this is the output of such a thing, right? And what I'm showing you here is basically what the human did. So we learned this thing by imitating what humans do while not having collision and driving on where we're supposed to drive on the lanes and satisfying the rules of traffic, so traffic lights, et cetera. Okay? And this is fully end-to-end trained. There is no human saying that, oh, we should do this type of behavior versus not. Which is typically in industry what happens is that every new capability for the planner, you go multiple months, you have a full team developing only that capability. Here you can just directly learn it. Okay? And I'm illustrating this with some fairly complex maneuvers that the motion planner has to do. Okay? And it learns all these complex things automatically, as I mentioned. All right, so now we know how to do motion planning, potentially in a learned fashion, right? And we know how to do joint perception and prediction. We can ask the next question, which is, well, can we actually do everything jointly? Right, now we have the pieces, right? We have gained the intuitions about these different tasks, right? So we are ready for the next generation of this thing. So I'm gonna show you the first generation of neural motion planners that we built. We are now in our third generation, I guess, which I will be able to talk about it quite soon, but not yet. So I will show you this one. So the idea here is that the motion planner basically is going to do detection, prediction into the future, as well as motion planning. And what I'm going to illustrate in the video is the detections are just bounding boxes. The predictions are longer-term horizon here, I believe it's 5 seconds. They're going to be these waypoints, okay? And the motion planner, so they share the same trunk of the neural network. And then basically, we learn to output a full cost volume for the planner. So that basically planning is nothing but you sample realizable trajectories that are physically valid, and then you evaluate your cost function. Okay? And you can do this extremely fast because your cost volume is just your neural net activations. And it's just indexing on those neural net activations for those trajectories. And then planning is nothing but I evaluate all the trajectories, and I sum what I index, and I basically take the mean. Those are operations that you can do with neural nets. So this is just a neural net. Okay? So you can train, again, end-to-end this thing. And the way that I'm going to visualize the cost volume is three-dimensional, so it's very complicated, but I'm going to show you here areas of low cost. And different colors are different times in the future. Okay, so I'm projecting this three-dimensional massive thing into 2 dimensions and only showing a thresholded version of this cost volume. Okay? And this will give you an understanding of what the car is thinking into what are possible behaviors. This is, again, trained end-to-end, whole detection, prediction, as well as motion planning trained end-to-end by imitating humans and satisfying rules of traffic and not having collisions, okay? And you see here, in this case, this planner didn't have a goal. So that's and it's on purpose so that you see the multimodality of what are all the options that I have, for example, when I arrive to an intersection. And once you pass a little bit, right, there is only one option. The turning is not anymore an option, and it learns this automatically. You see here also that it likes to change lanes so it's not the case here, but there is a whole bunch of examples where it likes to change lanes and ACC, and it's already planning for that, right? You can see that with the cost volume. So it learns these very complex behaviors all automatic without any tuning. For example, nudge, right, or a super nudge here is a very difficult maneuver. Again, it's just learning, and there is not really that many cases, if any, of this thing, but it can generalize. All right, so I show you a full end-to-end system, right? And one of the things that it was underlying is the fact that this autonomy system uses high-definition maps. One of the other things that we do in the lab is how can we create technology that will allow us to create these high-definition maps in as automatic fashion as possible, such that we can scale again to the whole world. And this is one of the, mapping is really one of the elephants or skeletons in the closet that people don't talk about, but it's really preventing companies from scaling to very far away, okay, to very big ODs. So we built technology that can create city-like 3D reconstructions, for example, by merging, in this case I'm showing merging cameras as well as LiDAR so that you can increase the field of view. So as I mentioned before, we also do a lot of the automation. So these maps have, for example, things like where are the lanes, traffic lights, all that stuff, right? And in this case, I'm showing you neural networks that we built that from only a few hundred examples, learn to create for highways like full road topologies. This is the fully automatic case, but they are built in a way that are human-in-the-loop friendly, meaning that a human could correct if they make any mistake, and it will recorrect itself. And that's the way that you get to this, from a very, very expensive human process of clicking, this is how these high-definition maps are done in industry, to something where you have high level of automation without needing you to be fully automatic, which is extremely difficult, and it's just the holy grail, right? And in this case, so I'm showing here what is trained. In this case, it's Arizona highways, tested on Arizona, and then we're going to go into San Francisco, hopefully in a second. San Francisco highways that are very different, no training example, no domain adaptation, out of the box. It can actually handle much more complex topologies. And this, from a machine learning perspective, is a very interesting model. It's a deep structural model. You can think of it as a marriage between graphical models and neural networks. But in this case, we have to solve for the graph. We don't even have the graph. And it's the lane topology, the graph. And the nodes basically tell you what are the attributes, like is this a merge versus not, as well as where exactly those nodes should be in space. Okay, so it's very, very interesting from mathematical perspective. Some of the other things that we done in the lab also, so this was offline. We also built high-definition maps online. This was one of the first things that we actually did at Uber, where basically, contrary to what you see in our competitors, we are able to, so this is, we can drive with no high-definition map. This is high-definition map on the fly, okay? So given the cameras as well as the LiDAR, we estimate all the lanes in the environment. And that's something that is different. Typically, you will see ego lane, maybe your lane next to us. Here is like the full map in 3D, not just 2D, okay? And we actually used to drive with this technology on highways with no maps, no a priori maps, for hundreds of kilometers with no intervention, okay? So this is actually something very, very robust. One of my favorite topics is that, well, life is more complicated than just this, right? The world changes all the time. So your maps can be, can go out of date quite quickly, and construction is something that happens a lot. These are captured during my commute. I walk to work, and Toronto is either winter season or construction season, right? And so there is a lot of very interesting configurations of construction, and construction is quite exciting. And so basically, we build also the online systems that are able to estimate on the fly where all the construction elements are in terms of in three-dimensional space. So we've used LiDAR as well as images, right, to get this very precise description of what these construction elements are. And for the cones, we can detect for the first time on average at least 150 meters from the vehicle that there is a little cone. And this allows us to, for example, slow down or start up an Uber that will allow us to change lanes with sufficient room so that we can do this in a safe manner. Okay. And this runs in real time on the vehicle as well, right? All right, so the last thing I want to talk to you about is simulation, right? So we saw autonomy systems, we saw some technology into how to build maps. I didn't talk today about localization, which is something that we also have a lot of efforts on. But I wanted to talk to you about simulation because this is something that is extremely, extremely important. It's very important for increasing the speed of autonomy development. It's extremely important for being able to do system engineering and testing, verify your systems, as well as to make the safety case, okay? And so I'm just illustrating here once more the autonomy stack, right? So because I want to illustrate, ideally we would like to test the whole system, right? So that we can actually verify and make the safety case. Now what happens in industry is the following, is that simulating sensors is extremely difficult. So what do people do? They chop down, right? And they basically start with bounding boxes. right? I'm going to simulate behaviors at the bounding box level, and then I'm going to input this to the rest of the stack, right? And what happens with this is that, great, you can test your motion planner, but in order to fully test your motion planner, you need to have a very precise description of the noise model of your perception system, and that's very hard. On top of this, you're actually not verifying the full system, because if you verify perception independent of motion planning, right, you might have a good perception system, a good motion planning system, but if their errors correlate in a bad way, then you can have an extremely unsafe system, right? That's why you need to do something different. You need to be able to simulate the sensors and then be able to test the full thing. Now, as you probably all know, right, simulating sensors is extremely hard. So what do you see typically in the literature? And this is from Carla Simulator. I'm sure that a lot of you use this, right? Is that what you see in the literature, right, is that you have artists that create virtual worlds. And given this virtual world, you have a model of rendering for the sensor, right? This is where your physics kicks in, right? And then you can render either cameras on the left or the LiDAR sensor on the right. Now, what happens with this is that it's extremely difficult to build realistic worlds, right? The movie industry or the gaming industry uses like hundreds of millions of dollars for smallest scenes that are realistic, right? So this is not going to scale to the whole world. And so what can we do, right? So the alternative is the following, which is at Uber, we have driven 3 million miles. So we have so much data of how the world looks like. So what we can do is build these virtual worlds from our observations of the world. And we can also build the assets and everything from our observations. And then we can compose the world to create these scenarios that we want to simulate. And then we can have a simulator where physics as well as machine learning can actually give you a high level of fidelity of what that simulation should be, okay? Which is very different than having artists doing something and then just physics rendering. All right, so this is just showing some of the reconstructions. So we can reconstruct the city scale, right? How our cities are. And this is very important because we can actually simulate particular intersections that are actually our operation domain if we wanted to, right? We can actually also capture, as we drive along, all the different vehicles that we see. These are actually reconstructed by us driving around standard logs that are not for simulation, that are just our driving, okay? And we have curated 25,000 of these guys, right? That you can see here the diversity of their appearance. It will be very expensive to have CAD models of this level of fidelity, right? And not only that, we also have intensity of our LiDAR, for example. So we can simulate that. We will need materials if we wanted to do so, right? So it will be even more expensive to generate this. And the shape distribution of these assets are actually quite diverse. And you see here, like all sorts of interesting examples, right? We can do all sorts of objects. We can do cyclists, pedestrians as well, right? And then basically, we can reconstruct the world this way. We have all these different assets. And then at generation time, you can decide, I want to generate a scene in this particular place in the world, right? With this particular traffic configuration. And then we're going to have reactive actors that are intelligent, right? And the EV is going to be placed on in that particular scenario, right? And then we can test particular scenarios that are of interest to us. And they will be very, very realistic. And then the way that we do rendering is that we basically have a physics model that does recasting. And on top of this, the AI system corrects such as the noise is similar to the noise of the sensor, right? So here we're using physics as well as AI, and the combination of these two things is actually very, very powerful. Instead of just giving everything to AI and hopefully this thing will do it. Okay, so this is our behavioral simulation. Hopefully you can see something here. So these ant-like things are vehicles that react to each other, are able to understand rules of traffic, etc. Right? So you can create these very complex scenarios of how different behaviors. And then basically what we can do is that we can then decide where, place the assets, do this behavior, and then test our motion planner. Okay? On the left-hand side, you see our simulation. On the right-hand side, you see the real world. So here we are placing the configuration of the assets to mimic the real world, okay? And what you see is that there is very little difference between the two. But what is more important is that on green, you see perception output from a system that is only trained on real data. And it's tested on the left on simulation and on the right on the real world. And there is almost no difference. Right? So this allows us to test on simulation. This allows us to create additional examples and train even further our systems. Now we can create safety critical things that we cannot capture, right? You don't want to capture for safety. But now we can test all that stuff. Now, what is interesting, I'm just showing this in the case of semantic segmentation. So if you train on real, you have a certain level of performance. These are per scenes. If you train using Carla, your performance drops a lot, right? This is 30% down or 35% down. And what happens is that then people are very excited about domain adaptation, right? Because, oh, there is a domain gap, I need to adapt, let's try to do something intelligent into how to bridge this gap. However, if you build a simulator that is very realistic, domain adaptation is not necessary. And that's what you see here. If we train on simulation and we test on the real world, the performance is basically the same, within 1%. Right? So this was quite interesting because I have a project in domain adaptation that I have to just basically stop it because you don't need domain adaptation. Now, so this is very good news, right? I mean, bad news for the project, very good news for us, because now we can use this for safety, verification, and all that stuff, right? And we don't need to do anything special. And I mentioned before, we can use this for training. So here is some performance when you train only on real, say 71%. When you train on a lot more examples on real, you can increase this. If you train on a few real and a lot of simulation, you can get to more or less the same level of performance of training at the same amount on real, right? And then you can further add more simulation, right? And get further boosting performance. This is with very simplistic techniques, right? So now there is, can do better and better and better, right? And basically get your systems to react to different scenarios. Of course.
So you take a single pass past a dynamic object. The BRDF, the BRDF should have an entire spectrum of results, right? And so if you're going to now ray trace or try to simulate a laser return from a different angle, for instance, how can you possibly have enough information from a quick pass in order to reproduce the LiDAR from many different angles?
So for the asset, there's a lot of things that we do in order to make them more dense. For example, we mirror them and we complete them in a way that is, we are able to get more complete shapes, right? Now they have some holes and stuff, and you will see a little bit more noise in our LiDAR. In terms of the intensity, here is difficult. And also this was Velodyne data where there is some crazy modulation of the intensity based on a whole bunch of things, including saturation and whatnot. So the intensity is not great. The geometry is pretty decent. And the geometry is sufficient for our networks to don't make a difference in terms of performance. So the networks are actually...
Shields and rearview mirrors and smoke plumes and all that stuff?
Yeah, so it's not a level of realism, right? But in terms of the networks per se, so our networks are based on BEV, so bird's eye view. They are pretty robust to not being precise. Some of the other networks that are more like projecting into image space, they are really much more sensitive to this. So that's also tied to which representation you have. But for our perception systems, there is, as I say, 1% difference. There's almost no difference. Yeah. So this is also like the networks are actually quite robust to certain noise things. So you don't need to have perfect rendering or perfect simulation for you to be able to do this. Cool. So what we can also do is, in this case, this is our reconstruction of the environment, and we're going to add two assets that weren't there in the first place. We are adding this large vehicle, and we're basically creating safety difficult scenarios. In this case, this is one of the typical cases of you want to see how you react to somebody coming just into your lane, okay? And this is just added on top of the traffic that was in this particular scene, okay? So we can create this in our simulation. We can use our assets, and then we can render as how the simulation will look like given the LiDAR, right? And then we can test our perception systems. And you can basically do this at scale. These are in different areas of, in this case, different cities. We place exactly the same type of scenario now with variations of the parameters, etc. Right? So you can create all these different test examples for one particular, say, scenario family or a scenario type that you want to test. Okay, so this allows you to do this at the scale very, very easily. And I guess we call this LiDAR sim. So you can do similar things with images. Now, images are much more difficult to be able to simulate in a way that the networks don't see a difference. And I'm going to start by asking you a question. One of these vehicles is fake. Do you know which one? Who thinks is the big vehicle on the right? What about the one in front? What about this guy here? The pickup on the back? Huh? Right, so now the projector is helping me as well, right? But basically this car here is fake. So the way that we do this is the following, it's the same idea, right? We have driven so many miles, right, that you can take what the logs, right, what the car has seen, and then you can in-paint things, and we're also doing stuff that removes things. And this is the way that you can get very, very good background, right, as well as you can test like different things. Now, the way that we do this is not just image-centric. We do it in a way that is consistent in three-dimensional space. And then you get the right size of the vehicle, right, the right orientation, as well as you can have image simulation consistent with LiDAR simulation. And this is extremely important for us because we need to test systems that take multiple sensors as input. Now, this is still work in progress. There is a lot to be done in this. Just showing you another example. Here you can see a little bit more of the issues, but basically you can crop, deform, pace, correct. That's basically the idea, and you do it in a way that is three-dimensional aware. Okay, and that allows it to give you more level of realism. And I think that this direction is actually a very good direction in order to get the level of realism that will allow you to train networks better and better. Cool, so just to finish, so self-driving is something that, when it's there at the scale, it's gonna have a lot of benefits. There is 1.3 million deaths every year on the road. So this technology is going to save a lot of lives. Also, it's going to provide mobility for many people that actually, as the population gets older, right, that they don't have a way to move from point A to point B. Ideally, it's going to reduce the cost of transportation, and it's going to allow us to also share the resources and have less congestion. Now, one thing that is important is that we can develop this technology and be very excited about the technical challenges, but if every one of us goes out and then buys a self-driving car, basically we will not be able to move anywhere. Right? So it's really on the combination of public transit, car sharing, and ride sharing, I think, where we can actually share all these things and be able to move in a way that we want. And I'm just going to finish with a video for you. Imagine the future. You hold your Uber, your self-driving car is dropping you there. Beautiful building, and you press the elevator. So we have a big program at Uber on these flying things. I'm very, very excited. For many commutes, this makes a lot of sense. The world is three-dimensional, right? 2D might be congested at some point, right? This might seem like science fiction to you. However, if you think about it, this kind of technology is much, much closer than you think. you.
Who wants to take the first one?
Thank you for the talk. You said before that there is a reasoning layer above all the intelligent mechanisms. So let's consider a situation that an accident is inevitable, and we're not even talking about whose fault is this. Let's consider that a person is thrown in front of the car, and is there a sequence of priorities of what to do? Like something bad is going to happen. I either hit the person, I hit a car, I flip and kill myself. So is there a sequence of priorities? Is there something to like minimize the situation?
Yeah, so let's see, without going into the trolley problem, which is why you're hinting but not hinting at the same time. Let's see, so without going into how you set those priorities, right? You need to, when you do motion planning and something inevitable is going to happen, you need to think about potentially the consequences of the choices, right? And maybe those consequences is something that you can use in order to guide what is the best decision for your planner to make. Now, this is also a way, formulating this mathematically also can allow potentially regulators, right, to tell us what to do in which situations if they want to solve the trolley problem, right? But there are ways to encode this kind of thing, right, within the motion planners, yes. Thank you.
Thank you for the talk. And for the CV simulation, the camera image simulation, and I imagine you guys also do some stereo matching to get the depths. Does the stereo matching perform the same on the fake car and as well as the real car?
So without going into how we actually do this, so for us, we have more than just a stereo. We have a set of cameras, we have LiDAR, so we can actually have a fairly good estimation of 3D, and you can exploit that to do better simulations. There is a whole bunch of work in the lab now going into different representations that allow you to do so.
Yeah, and also for the LiDAR simulation, the intensity also varies on light conditions and temperature conditions.
Yes.
Is that also included in your simulator?
Yes, so we did a lot of work into trying to model, given some of those factors that you can measure, like also incident angle and saturation of the whole scene and things like that. But for sensors like Velodyne, so far was impossible to get better than noise level. For better sensors, you can do things like that. Now, this is very difficult, and to your point, this is something where to get like very precise intensity is pretty hard. The question is, how important is intensity for the networks as well, right? And can you mimic the statistics of the networks sufficiently close so that that's okay?
Yeah, but you guys use the intensity for line detection, so I assume that will be somewhat important.
Yeah, so we did some experiments, I guess, we didn't include in the paper, where you can do line detection with this. And what the results that you see here is just nearest neighbor. And if your logs are not too crazy, then that's sufficient. But obviously, you would like to do other things if you want to go to test different weather conditions, and then you can build more complex models, and that's sort of like next generations of this tech, yeah. There is a lot to be done here. This is nothing of this is solved, right? This is sort of the next generation, and then we just need to continue iterating into more and more things, yeah.
Thanks.
Yes.
Oh, sorry. Yeah, thank you for the talk. I was wondering, as the use of neural networks increases throughout the stack, whether you see the need for maybe simpler fallback mechanisms to still be in place, or whether you think these networks will become so robust that even those will not be needed anymore.
Yeah, so a very good question, right? So the way to get to, where single algorithms are to the performance that you need, right? One way to get there is to have to build a system that is robust. Right? And typically, the way that you think about building systems is that I'm going to have, if this mechanism failed, then I have another one. If this fails, I have another one. If this fails, I have another one. Now, if you think about those decisions, the question is, are those decisions something that you hand design? Or is that a single system that you still train to be robust? Right? And to me, this is just the scope of your system. Right? So it's not different than any of this, right? But the decision into which system to trust is the one where the bottleneck is, and one has to be very careful. Yeah, fantastic question.
Can you say something, or are you allowed to say something about the scale of this learning problem, right? Like, how big are the data sets that you have to generate to get to that 90%? Or how long does it take to train them? Or I don't know.
Let's see.
Is this something that is feasible to do in a lab, or there's no way? What are we talking?
Let's see. So on the papers, we showcase what in academia is large-scale data sets. They are not the production data sets. The production data sets are bigger. I can't tell you the scale of the production data sets, obviously. There is so many competitors in the audience. But we also, for all our systems, or almost all of our papers, we also tested on the public benchmarks so that you can also see. And what is very interesting is that we develop in our internal data sets, and we just tested with really no changes on the public. And that allows us to show how it generalizes to changes of sensor configuration, different traffic, etc. And so far it's been like it generalizes really, really well. We don't need to do much tuning at all. Yeah, sorry for the half answer.
So let me ask you a naive question, somebody that doesn't work in the space. I always has been curious if it's a herd phenomena that it seems that nobody's using communication with the infrastructure.
Yeah, great question. Let's see, what can I say? One of my favorite topics these days is V2X communication. I didn't put anything on the talk. You will see very, very soon from the lab coming some very interesting work on vehicle-to-vehicle communication, of how learning what information to transmit, as well as how to aggregate the information to get much better performance and safety than single systems, which is very exciting. And the same kind of thing you can do, you can use vehicle-to-X. For example, I'm interested if we could use things like cameras placed in intersections, stuff like that, for the blind spots of the vehicles, etc. I think this is an extremely, extremely interesting question. There is privacy concerns and other things. So there is safety concerns as well in terms of every time there is V2 something, if somebody hacks. So we are doing also a lot of work in adversarial and robustness to adversary stuff. So you will see a lot of that stuff as well. So that's sort of the next generation coming. Yeah. It's a very, very interesting topic. There is so much to be done. But we have some very, very interesting neural net designs for compressing tiny messages that gives you a lot of stuff.
You mentioned that you are creating some maps on the fly.
Yeah.
How do you deal with the uncertainty in that case if you are going from A point to a B point without the classical closing loop? Are you using some kind of local reference frames, or how are you dealing with the uncertainty position of all the 3D elements?
Yeah, when I say without maps, so I didn't, I guess, explain properly this. So there is two levels of maps. There is the regular map that is the one that your phone, whatever, uses, right? That you typically use for the high-level planner, right? And this says from A to B, these are the streets or whatever where I want to drive. And for that, you need some sort of localization, right? Otherwise, how are you going to get to where you're intending to be if you don't know where you are? Now, the type of maps that I'm talking about is for self-driving, you use as an additional sensor the map of the environment that has all this very useful information like lanes, where the traffic lights are, where the crosswalks are, etc. And those are the type of things that we can generate on the fly. But you can, if you need to go from A to B, you need to know where A is and where B is, obviously. So you need some sort of something. Makes sense? But for self-driving, when I say on the fly here, I was referring to if we don't have the high definition map, which is the one that is very expensive. The other one, you can use commodity, OSM, TomTom, Google Maps, whatever is your favorite.
Yeah. All right. Well, any other questions? Maybe on this side.
There is one over there. It's the adversarial example, right?
Exactly.
Thanks for the talk. So right at the beginning, you mentioned compositionality was a desirable attribute of this sort of factored system. And you said we gained all these advantages by going back to the monolithic neural network. Have we lost compositionality? Is that the compromise that we're making?
Why do you think we lose compositionality here?
Because if the network is spitting out a cost volume at the end, you're not able to compose the individual predictions of the bounding boxes of the cars and their trajectories.
Yeah, okay. So,
what is the representation that's getting passed through?
So in the neural motion planner, I guess in the one I show here, you have some multitask approach, right, where you do detections, you do predictions, and then you have a header for the cost volume, and they are separated. In generations 2 and 3, that's not the case anymore. So you can bring back that and be consistent, and the compositionality is there. Yeah.
Thank you.
Great question. Yes.
Can you perhaps just shortly elaborate on where is the localization stack here, and perhaps also if you take into account calibration of the sensor?
Yeah, let's see. Sorry, just give me 1 second and maybe I can show you that. Cool. So localization, so what you need for localization is 3 things. Low cost, real time, and high accuracy. And the way that you can do this thing in a cheap manner is you can learn to do intensity-based localization that is very, very precise. So the idea is that you have a map that is just an intensity map of how from the top the world looks like, right? And you have the online later sweep, and then you basically learn too much, but you do it in a way that you can compress the map so that the whole North America fits in a small disk, okay? And the idea is that basically you have a recursive process where you're matching under uncertainty. This is the way that it allows you to not require even calibration of the sensor, which is typically what is required for these kind of approaches. So you learn to be robust of calibration and things like that. You learn to compress so that you can fit things, and then you match with neural nets. And there is a whole bunch of cool design into how you can do this in a few milliseconds with some specialized kernels. So we build this kind of approach for localization, for example. We have also built, there's a whole bunch of papers from the lab. We can build things that only use lane markings as well as signs. That's actually quite useful if you do ADAS. You can also do more more geometry-based localization, etc. But this is one that works extremely well with, on average, is 3 centimeters away from the truth and at scale. So hopefully that answered a bit.
All right, I think we can continue the conversation outside in the reception. Thank you very much, Raquel.